Hi, everybody. Thanks for being here. I'm really excited to talk to you today about building a new kind of SLO for machine learning systems, specifically productionized machine learning systems that run in web services. This talk is going to be really interesting because it's largely hypothetical. I really like to talk about SLOs. I really like to talk about SRE theory because it inspires the inner mathematician in me. Right. So as a little bit of background, I'm a data scientist. I'm not an infrastructure developer. I hardly know what a Kubernetes is. But I spent a long time building and analyzing real-time control systems. I studied aeronautical engineering and computational mathematics, and I worked for many, many years building and analyzing and simulating and modeling systems like aircraft and spacecraft and powered prosthetic limbs and all sorts of things like that. And when I started to look at the types of work I was doing and the term data scientist came into being, I started to look at what data scientists were doing and saying, well, we're doing actually kind of the same things, except they get paid a lot more money. So I became a data scientist. And when I started to discover SRE theory about 5 or 6 years ago, I was really drawn by the mathematical and the sort of computational nature of building software systems in a way that I felt was very important, right? So coming as like an aeronautical engineer where quality is really important and reliability is really important, I was really actually happy to start seeing a world of software development where those things also matter. I really like SLOs for a number of reasons. And one of them is that I kind of have this like old-timey like sense to myself, right? I still remember when people used to buy products based on the quality of those products. It used to be a selling point. You would buy a TV knowing that like this is a really high quality TV. The manufacturer has a warranty. All of that's going to be really good. So I'm willing to spend a little bit more money for it. Maybe we still do that sometimes, but really, honestly, these days not as much with globalization and nothing is high quality and everything is made to be disposable. But SLOs kind of bring me back, right? Because you're actually saying, here is the quality of my software that I'm going to commit. Here's a promise that I'm going to make. Here's the guarantee. It's on the box, right? SLOs give you the ability to write great SLAs, and that allows you to communicate some meaning of quality that should still be important to some customers somewhere. And what I like about SLOs is that they connect the behavior of your system to something that actually has expressible business value. You're saying that uptime matters. You're valuing what the consumer, the customer is doing with your system. And also SLOs are there to help you guide product engineering decisions. It's a way to let you know when you should be doing better at engineering, when you should be improving, when you should be doing something different, right? And these are really positive things in my world. The challenge is that a lot of companies, a lot of people have read the SRE book. They've implemented SLOs without really thinking about them. I see all these things like, I build a lot of data engineering systems in my day job, and I often ask people, what's your uptime? And they say 24/7. And of course, we all know 24/7 is not possible. And they say, well, we can't do 24/7. They're like the 99.9%. Really? Do you know how hard it is to engineer a data system to be available 99.9% of the time? Do you know how little downtime you have per year? One Postgres upgrade is going to eat your error budget. Do you really have people that are doing BI queries at 3:30 in the morning? Is that really necessary? And so a lot of people are just doing SRE based on the book without thinking about the business value. And one of the areas that they're doing that in is building SLOs around machine learning systems, productionized machine learning systems. So I don't really need to explain the values of SLOs to you because here you are at SLOconf. I hope that you all see the world in much the same way I do. What I do want to tell you, though, is that we've really broken it for machine learning systems. Availability and latency are core SLOs for a lot of software services. And the reason that these are core SLOs is because a lot of software services make a lot of sense when you are doing high volume and with deterministic outputs, right? Your search engine should work every time. Your login engine or your login system should work every time. The value of that, each request, is probably quite small, but availability and latency communicate consistency. And when you have consistency, that means you have a higher quality product, right? And so when we design systems like that for scale, we're designing for lots and lots of small marginal value transactions, right? And these SLOs make sense for that. The problem is that some systems are not consistent, and they're not designed to be consistent. Systems that have to inherit a space of uncertainty, systems that are fundamentally nonlinear, are really difficult to have consistency around, right? Humans are fickle creatures. We are not consistent day to day, hour to hour, person to person. Right? Really hard to build SLOs that communicate value if those SLOs are built around consistency, if you have an inconsistent and sort of chaotic system. And so the challenge with a lot of machine learning systems is that it's really hard sometimes to know what the right output is. It's really hard to know if you've got the best output. And sometimes the things that we need to measure, we can't even measure at all. So we have a number of problems. I'm going to break it down by each of these problems. And I'm going to give you some metaphors and examples of how to think about what I'm trying to get to. My goal here is to build up to a theory. Now, I'm not going to give you all of the answers to this theory, but I'm going to try to walk you as close to the edge as I can. So the first of these problems is unmeasurable states. So imagine building something like a fraud detection algorithm. Fraud detection, you might want to say, is this customer a real customer or are they a fraudster? And I might want to build a binary classifier that tells me yes or no. And I might have a bunch of training data. So I train my model, I validate it, I put it into production. What's great when you build a binary classifier is you can come up with something like a confusion matrix. And normally in the little quadrants of the confusion matrix, we have probabilities. But because I'm talking about business value, I'm going to put dollar amounts there. And so with our classifier, we might say that the average customer is worth $100 and the average fraudster costs us $500. And if we build an algorithm that misclassifies a true customer, then we might miss out on their $100. We also might inherit some reputational loss because they tell their friends. And so the value of a true or a false negative is higher than the value of the corresponding value of the true positive. And then, of course, if you assume that somebody is a customer, but they're actually a fraudster, you're going to do a lot of damage. But there's no loss and no gain if you actually correctly identify the fraudsters. And so this is the kind of thing that we want to actually get into. The problem is we can really only build this matrix for our past historical training data. We can't actually build this matrix for the real data. Why is that? A couple of problems. One, fraudsters take a really long time to identify most of the time. If somebody is a good fraudster, you may never know that they're a fraudster. Otherwise, it may take 60, 90, 180 days for you to determine if that customer is real or not. Right? Maybe they're just there to scam you with returns or whatever. Likewise, if you flag real customers as fraudsters, they go away, they're never coming back, they're never telling you, you are never going to hear from that person again, unless they yell at you on Twitter. And so we don't actually even know how many people we are misclassifying most of the time, because we don't know how, we don't know the things that we can't see, we don't know the things that we can't measure, right? So in order to evaluate the actual performance of our algorithm in production is a much harder problem than evaluating the hypothetical performance of the algorithm trained against historical data. So we have this problem of not being able to measure the full spectrum of what this algorithm is doing. We classify people as fraudsters or not. The fraudsters are never allowed onto the system. We'll never know what percentage of those were errors. And so it makes sense if we want to develop an SLO around model performance, but if it's really hard to measure those outputs, either directly, quickly, or easily, then how do we actually do this? How do we actually build an SLO around model performance? We can kind of look at what it does in the benchtop in the laboratory, but it's hard to do it in our real production systems. There's a similar example. Now I'm going to come to these spaceflight examples, not only because I'm an aeronautical engineer, but because there's a very good reason for this, for it underlying this talk. How do you measure the temperature of a rocket plume? You can't stick a thermometer into the rocket to say, how hot are you? It's really important to know how hot the rocket plume is because it correlates to engine performance. And if it's too hot, then your rocket blows up and you don't go to space today. And so you might think about measuring something else. You might think about measuring the temperature on the bell, or you might think about measuring the velocity of the exhaust, or something indirect, right? And that's actually what we do. And the way that this works is usually we measure something, we look at something that we can measure, and we have a model for how the thing that we want to measure translates into the thing that we can measure, right? And so what we do is we have some estimate of where we are, and we have some model that takes in the inputs and the estimate and gives us a prediction of the state. And then what we do once we have that prediction of the state is we take more measurements and we compare the predicted state to the measured state, and there's some uncertainty here, but we come up with an error estimate. And that error estimate then allows us to update our estimate of state, which we then use to be the next estimate of state in the next iteration of this loop. And we do this over and over and over for all time. And so instead of measuring the temperature of the rocket exhaust, I'm measuring the temperature of the bell. And then I know that there is some thermodynamical model of how the bell heats and cools. And from that, I can sort of back out what the temperature of the plume is. And I might use other things like the acceleration of the rocket, right? If the temperature plume estimate says 98%, well, I better be accelerating as if the rocket is giving me 98% thrust. If I'm not, then something might be wrong, right? And so we do this all the time. And so rather than thinking about measuring directly what we're trying to do, we look at the observable effects of the behavior. And if we look at the observable effects and we compare that to what we are seeing with our model performance, we can actually tell something about the quality of the model, right? So actually what we want to do is we want to think about how does our system work vis-a-vis the predictions that we have about the system, right? So we can think about if the model is really, if it's throwing a lot of errors, then we have a low quality model. I'm going to come back to this idea. But the problem is that not every system is quite so simple. A lot of systems, you have a situation where reality can only happen once. Actually, all of reality can only happen once, but there are times that we really wish it didn't. So let's take a different example. For example, a recommendation algorithm for an e-commerce site. I buy a product, it recommends me other things that I might want to buy, for example, a social media company or a blue check mark. And based on what the system knows about me, my past behavior, my past purchases, my user agent information, cookies that are in my browser, whatever, we can make some guesses about how we might act. But the thing is, I don't get to recommend you everything in my catalog. I really have to pick 2 or 3 things. So the question is, how do I know if I've picked the right 3 things? If you buy something, does it mean the algorithm has done good? What if you were to buy something different? If you don't buy something, does it mean that the algorithm is bad? Yeah, maybe not. Maybe I just didn't have the money. Maybe I just didn't have the inclination to buy those things at that time. So it's really actually hard to see whether we are making the right decision in a possible space of infinite decisions. And the problem is you can only measure that effect once, maybe a couple of times if you have multiple steps in the flow. But generally speaking, you have a very finite number of chances to measure a potentially infinite number of combinations. And so we can't probe the multiverse. We can't look into what alternate histories or alternate realities might exist. And so we're stuck. We're stuck with trying to guess the performance of our system based on the one thing that we can measure out of many, many, many things. So how do we actually try to build an SLO around that? So if we can't look at the other outcomes, how do we know if we could be doing better? Or how do we know if we're doing as good as it gets, right? These things are really hard for us to understand. So what we actually do in practice is we don't worry about each user individually. We look at distributions of users. We look at distributions of user properties and distributions of outcomes, and we try to come up with correlations. And we do this in very high multi-dimensional spaces, and we use a lot of mathematics to try to come up with these things. And this is sort of the foundation of how data science works, right? And this is fine. We look at randomness across many customers. Sometimes this leads to a bad user experience. I'm sure you've seen things like if you get two people in incognito mode and you go look at what's trending on Twitter, you get two different results. And why is that the case? Well, it's because they're trying different algorithms, different samplings for different users. It's not a deterministic system, right? Fundamentally, machine learning systems are non-deterministic. The third problem is that life doesn't sit still, right? You might have a really great idea about what you want to do, and you might train a really great model, but the thing is your training data is almost always in the past. And when you do that, you're making a really big philosophical leap of faith. You are making an assumption that the future is going to be sufficiently similar to the past, that your past data is good enough to predict the future, or at least to be useful. Now, we know that that's not true. We know that there are step changes in user behavior. For example, in the COVID-19 pandemic, user behavior totally changed. You had users behaving in one sort of generalized set of ways, and then March 2020 happened, and then everything was totally different. And if you had a machine learning algorithm in production at that time, it probably gave you really crappy performance in the first months or weeks of the pandemic because it was expecting a totally different set of user behaviors. So how much money did you lose by not having a good enough recommendation engine? Nobody really knows because we can't probe the multiverse. But what we can do is assume that things are going to change. And that means that it's really hard to create a baseline for an SLO. It's really hard to measure it against something because the thing that you're measuring against is constantly at risk of movement. That means that we need to create an SLO that moves with our reality. When we talk about this in the data science world, we talk about things like data drift. Data drift means changes in the underlying distribution. And data drift is not always so dramatic. Oftentimes, it's very subtle. And so when you look from month to month or week to week, your distributions might change, but they might only change slightly. And it's small enough that if you compare your model performance from this week to last week, it's good enough, and it's good enough, and it's good enough, but then things can degrade over time, right? You might be having a really consistent recommendation hit rate, but maybe you could be doing better, right? And so maybe you never even know because the data might be drifting in a way that would be favorable to you, but you're not actually catching it. It also might be drifting in a way that's unfavorable to you, and you might not be catching it, right? So the difference of these distributions over time is actually really relevant. That makes it really hard to build an SLO when you have that moving baseline. So let's bring this all together. So we have these three problems, right? We have things that are unmeasurable. We have a potentially infinite number of combinations of which we can only really measure one. And we have a constantly changing baseline. So if I want to create an SLO that measures the value of the product and that gives me some sort of gradient to inform my engineering decisions of how to make the product better, these things make it really freaking complicated to do that, right? So why not just give up? Why not just use latency and availability like everyone else? The problem is that it doesn't actually then connect to product value, and it doesn't give us any indication of where we should or how we should re-engineer to improve that quality, right? If I wanted to create a really high availability, low latency fraud detector, I would just do, is fraudster return false, right? And it's going to be right a lot of the time because most of my customers are not fraudsters. But is this really what I want to be doing? Am I really supposed to be optimizing around this type of SLO? I don't think so. So what we actually want to do is figure out a way to measure the performance of these sort of chaotic, uncertain systems. We want to do it in real time, and we want to do it in a way that tells us how to engineer better. Right? The good news is that we know actually how to solve this problem. The only thing you need to know is how to go to the moon. Now, we've been to the moon. We can actually send big rockets up into space that don't blow up. And we actually did that where we landed people on the moon. And we did this 50 years ago. Now, we did this 50 years ago with the thanks of an algorithm called the Kalman filter. The Kalman filter is a way of estimating state. When you have the presence of uncertainty, the Kalman filter is able to take a model and take a characteristic of uncertainty, make a prediction, compare that prediction to new measurements, update your estimated state, and then to do that all over again. This is used when we have really hard problems like how do you measure the temperature of an exhaust plume of a rocket? Or how do you track where your space capsule is on the way to the moon? There's inherent uncertainty in all of those measurements and all of our observations, and even in the behaviors of the system. The Kalman filter is really interesting because it uses this pattern, this predictor-corrector pattern, that's really common in numerical computing. It's really a great way to understand how to measure, monitor, and control dynamical systems. Now, Kalman filters are great when you have things that are linear and when you have noise that is Gaussian. But I started this talk off by telling you that we are looking at things that are highly nonlinear, and the noise characteristic almost certainly isn't Gaussian. So what can we do? The great news is that there's actually lots of different types of Kalman filters. People have really taken the mathematics of this and extended it into all sorts of different domains, right? So if you have nonlinear systems, we have something called the extended Kalman filter. If you want to do error detection, if you want to measure how your input states are affecting your outputs, and you want to try to isolate which input states might be most responsible for the behavior you're seeing, we have something called a constrained Kalman filter. And if we have things that are highly nonlinear or that are not Gaussian, there's something called an unscented Kalman filter. All of these things are being used all the time, but maybe not for this. So when we're doing a Kalman filter, when we're implementing a Kalman filter in a control system, what we're actually trying to do is we're trying to minimize this error estimate. We're trying to minimize what we call the residual. And the way that we do that is by trying to also improve our model, right? Sometimes we can just implement a Kalman filter to give us, more accurate state estimates, but we can also use these systems to do things like fault detection. We can use them for things like adaptive model improvement. We can do all of these things using this filtering technique. It's a very powerful concept. But the problem is that I'm not actually telling you anything that you don't already know. If a model underperforms, then we should improve it. What is this telling us, right? Like minimize the error, and that means that your model is doing better. But how do we know how to make our model better? How do we know in which direction we should take it, right? We can't just throw a bunch of computing power at the problem and hope that something works out. Because if you do that, I'm sure you're going to make somebody like Databricks very happy, but you're going to make the value of your product become marginally lower because it's so expensive to do it. The actual answer to this is so simple once you realize it, that it's actually painful. You use a second model. How do we compare against the baseline? Well, create a different model with a known character that closely maps to your reality and measure your model performance against that. Use a different model that has a characteristic that you understand much better and use that as your baseline. We actually do this in physical systems. The models that we use are not always correct. There's the famous George Box quote, which I don't need to repeat, but any model is sort of a proxy for system behavior, right? And so we assume that there's error in what we're doing. We assume that the model is not a perfect representation of what we're trying to do. Of course, if I could make a perfect representation of what a customer is going to do or what a user is going to do, I wouldn't need to do any of this because I would have that black box oracle. So it's okay if there is some sort of error characteristic. We can manage that. We can handle that. We can quantify that and optimize around it. And you might think, well, Emily, if I'm just using a second model that has maybe a less advanced but a known characteristic, aren't I just going to optimize everything back down to that model? Not necessarily, because using these techniques, we can actually start to decompose things in really interesting ways. So one way of doing it is creating what are called filterbacks. Imagine you have a system that trains on things like customer purchases and user agent and customer demographics, right? And you build a model that incorporates all of those things. Well, you can actually build 3 models, and each one of those models leaves one of those properties or sets of features out. So you have a model that excludes customer history, you have a model that excludes user agent, and you have a model that excludes user demographics, for example. And then you compare your new model, your production model, against those three. And the one that is giving the most wildly different results it means that whatever it's excluding is the most important thing that you have that you should be using to improve, right? So if I give two models that include purchase history and one model that doesn't include purchase history, that's giving me this sort of process by elimination that helps me tell which direction I should improve, right? And so we look at those residuals for each of these things, and we look to see what the impact of this is. The other thing that you can do with this is you can actually train a bunch of models on a bunch of different data that kind of covers your data drift. You can come up with smaller data sets that incorporate that data drift, or you can synthesize that data drift and train a bunch of different models that look at those different states. And when you compare your current model against the ones that are trained on the different states, you can actually see, oh, maybe my data is drifting, right? So you're able to detect much more quickly in real time if you are having data drift issues, or if you are having sort of feature imbalance issues that might lead to different sorts of types of model performance. And I mentioned earlier that we're sort of statistical creatures by nature, right? Two people who are very similar may react very differently given the same set of inputs. Give me two slightly different sets of inputs and I might react very differently based on a number of factors, right? We are very statistical and nonlinear creatures. And there is a Kalman filter that handles that. It's called the unscented Kalman filter. And what's interesting about unscented Kalman filters is that they were so named by the guy who invented them because he was staring at a stick of unscented deodorant and decided to use that as sort of a joke, thinking maybe, you know, a bunch of people will see, oh yeah, unscented, that's exactly the right word. Turns out that's exactly what happened. The name has stuck. It has nothing to do with scent. It has nothing to do with odor, but that's what we call them. And they're really interesting in how they work, because what you're doing is you're taking a sampling of your inputs and you're comparing it to a sampling of your outputs after being run through this nonlinear process. And rather than measuring the residuals directly, you're doing this sort of statistical comparison, which is exactly what we want to be doing in machine learning systems in production. We want to be comparing the statistics of a sampling of our users to a sampling of the outputs and looking at the model performance in this sort of statistical way. So this has been a lot of hand waving. In fact, if you see my little face in this video, I'm actually literally waving my hands. I've been doing it for a long time. And the reason is that I can't teach you the advanced math in 40 minutes that I need to do in order to establish this theory. So I'm giving you a lot of like high level stuff. So maybe you're here like, Emily, I've sat through like 20 minutes of you rambling about mathematics and rockets and going to the moon. What's the SLO? The SLO is your residual. It's your error estimate. If you come up with a system that is able to create this predictor corrector type of behavior, and you're able to create this error estimate, what you are able to do, much like what we do with latency or availability, is you're able to create a real-time metric that has a nice window trailing capability that tells you exactly how well your model is performing compared to a baseline. And this is a huge step forward from looking at the open loop static behavior of a trained machine learning model and saying, well, its precision and recall are this, or its area under the curve are this, or whatever metrics we want to come up with. Because this system is actually going to be able to measure live in real time how our models are able to perform. If we can do this, if we can create a way to compare our residual error, and we can use multiple machine learning models in our production environment instead of just one base model, this might actually help us connect our data science efforts to a product value and to the performance. And it might also help us understand when and how to improve our systems, because we're comparing against things that we can track in a real and concrete way. This is a step forward towards building a better SLO for these types of non-deterministic, highly nonlinear systems. So the question is, has this actually been tried? Have I built this? Yes and no. These systems are used all the time in real world engineering things. We use them to go to the moon. Kalman filters are in your cars, they're in your cell phones, they're in your medical devices, they're in your televisions, they're all over the place. It's a very, very, very fundamental algorithm. But I've never actually seen somebody try to implement this by treating a software system as a dynamical system with a user in the loop. I've never seen somebody try to create a closed loop way of doing this sort of performance monitoring, with one exception: reinforcement learning. In reinforcement learning applications, we're actually doing something very, very similar to this. We have a model, it makes a prediction, we measure the outputs, we measure the response, we update that model in response, we learn as we go. It's sometimes called online learning. And there's a natural sort of filtering behavior happening in these systems. Now, reinforcement learning systems are still fairly complex to implement, but coming up with a residual estimation type of method would be much simpler to implement. I've never seen somebody do it. I still don't know, as I sit here before you, exactly how we would construct the SLO. What I do know is that we've used these things even with AIs and machine learning and neural networks in the loop for control systems, and it works fantastically. I built many algorithms for failure detection and fault detection that use things like constrained Kalman filter banks to understand the performance of my machine learning system in production. I just never put it into a software system like a product recommender or a fraud detector. There's no reason that we couldn't, and I bet that you could. So I'm going to end with a challenge. Maybe you can be the first person to do this. Maybe you can go out and learn all of the mathematics and the statistics and the probability needed to do this. And maybe you've already built something that is kind of close to this, but maybe you just need to formalize a little bit to tie it all together. I would love to hear it if you're the first. Moreover, I'd love to join you to be that person that can do it. So if you want to get together in a hackathon and actually try to build something like this, I'm game. Hit me up in Slack, hit me up on DMs and social media, wherever. I'm not going to say which sites. You can find me. I'll fly out. We'll do a weekend. We'll get some pizza. Let's build a Kalman filter based SLO for a machine learning system. Let's see how it works. I'm super enthusiastic to do this because I really believe that we can do much better than just tracking availability and latency when it comes to highly nonlinear deterministic systems. So that's my challenge to you. Let's build something cool. Thank you very much for sticking with me through all of this. Have a great conference.